Good day, everyone. So we're going to start. The next few lessons will be some new integration techniques. If you're a Calculus BC student, these will be new for you. Now, just like the whole approach to using substitution or U substitution that we were reviewing last time is all geared towards reversing derivatives done with the chain rule. This method we're going to talk about today also is specific to reversing a particular type of derivative, and that is a derivative uh, using the logarithm rule. And so we're actually going to start today's lesson with reviewing of that method and look particularly what the typical answer to that kind of problem looks like. And then the main emphasis of today's lesson is how to actually algebraically reverse it. So I'm going to start today with looking at a derivative where the two parts of this function are logarithms. I've got a logarithm of x plus 3 multiplying by 2, and I've got a logarithm of x plus 1 all multiplying by 3. And let's just take a look at how this works. Remember that the primary rule for derivatives of logs is this one. If it's a logarithm of another function, we usually write log of u. The differentiation rule is the derivative of the natural log of u is u prime divided by u. In other words, it's the derivative of the inside of the log all over the inside of the log. In this case, that's what happens on both of these, and in both of them, there's a multiple of 2 or 3. So this derivative is going to end up looking like this. 2 times 1 over x minus 3, because in this case, your u is x plus 3, and u prime is 1. And this one is 3 times 1 over x plus 1, because in this one you can think of u as x plus 1, and its derivative is 1. So if I wrote it now as just 3 over x minus 3, sorry, 2 over x minus 3, and then 3 over x plus 1, most of the time that is how we would leave the answer. However, today let's put these together, which means we want to make a common denominator of x minus 3 times x plus 1. And that would mean that the first fraction would have to get multiplied by x plus 1 over x plus 1. And that would make the upper left corner 2x plus 2. And then the other side, and I'm sorry, this plus became a minus, it should be plus. This side we need to multiply by x minus 3 over x minus 3. So that would become 3x minus 9. And sorry, that plus also. Plus 9. So my grand total in the numerator is 5x plus 11. And it's all over the denominator, x squared. And if I multiply this out, it's going to be x squared minus 2x minus 3. So all told and simplified, this might be how we write it. So the lesson today would be, how would I know that this is the derivative of these two logs up here? It seems hard to know by looking at it. That's where it came from. Okay, so today the lesson will be, if I were to see that expression as an integral, the lesson today is knowing that that is going to be taking us back to these two logs up here. Okay, and so thinking about it in reverse, thinking about where we came from initially, this single fraction came from combining these two smaller fractions here. The two smaller fractions were 2 over x plus 3 and 3 over x plus 1. So the main objective here is, how can I get this big expression split back into these two little fractions? Because if I had those to look at, those individually might be easier to recognize as the derivatives of two logs, natural logs. So the main emphasis of this lesson today is to split this, a large fraction like this, into its two, what we call the partial fractions. So we're going to spend just 1 minute talking about that, because once we master that skill, the calculus part is actually the easy part. Okay, so I've got another expression like that one that I would like to split into partial fractions. The first thing I know to recognize that I can even attempt this is to know that the denominator of this fraction can be factored. And so I'm noticing that in mine, I can factor this down to x plus 3 times x plus 1. And so what I would attempt to do is try and find two fractions, one that has the denominator x plus 3 and the other one that has the denominator x plus 1. And we're going to presume that these two fractions are going to be in most reduced form, which means that the degree of the numerator will be even less than the denominator. And in order to be less than x to the first, it would have to be a constant. So I'm going to presume there are two constants, a and b, that are the numerators of these two fractions. And if I were to combine them together, I would make the fraction I started with. So let's remember how we algebraically combine them in the first place. If I'm going to make a common denominator, again, the easiest one would be to multiply x plus 3 times x plus 1. And that means that to form the proper numerator, this first fraction has to get multiplied by x plus 1 and x plus 1. So a ends up getting multiplied by x plus 1. And b, likewise, is going to have to get multiplied by x plus 3. And so now I really just want to key in on how does this going to end up being just x minus 2, the numerator of the expression we're trying to build. And so let's just write the equation relating the numerator now. X minus 2 equals a times x plus 1 and b times x plus 3. Now remember, when you're algebraically simplifying things or rewriting things, it's presumed that the new expression is going to be equivalent regardless of what number x is. So I could plug in any number for x and we would have an equation that relates a and b. However, we might not have one that I can just simply solve for a or b. So let's pick some convenient values for x that would allow us to solve for just a or just b. And the idea there is, let's pick a value of x and plug it in everywhere, but let's find one where maybe the b term will be eliminated or the a term will be eliminated. In this case, I would recognize that if I were to choose let x be negative 3, then the part with b in it is going to get multiplied by 0. And then I'd be able to just solve for a. So that's what I'm going to do. I'm going to let x be negative 3, and then negative 3 minus 2 is going to be negative 5. And on the other side, it's going to be negative 3 plus 1, which is negative 2. And then b is going to multiply by 0. So that we don't have to worry about now. And to find a, I'm just going to have to divide negative 5 by negative 2, and I would get positive 5 halves. Perfect. Now let's just go back to the beginning and try it again. I'm just going to draw some dividing lines here. Let's start from the beginning again and pick another value of x. This time, let's pick one that I can remove a with, and that would be minus 1. So the second time around, let's let x be minus 1 and plug it in everywhere again. So negative 1 minus 2 would be negative 3. A would then be multiplying by 0. And b is now going to be multiplying by the quantity negative 1 plus 3, which is 2. And so since the a term is gone, b is going to be negative 3 divided by 2. So now my two partial fractions are 5 halves over x minus 3 and minus 3/2 over x plus 1. Now I would probably write this another way yet, like maybe I would multiply it like this: 5/2 times 1 over x minus 3, and then minus 3/2 times 1 over x plus 1. And the way I'm writing it like this is because in a minute, the original expression really is going to be the integrand of an integral. And so by forming these partial fractions, I would now have two separate integrands. I would have this one here, and I might put the integral symbol right there. And I would put the integral symbol on this one right there. And now it's easy to recognize, I hope for you guys, that the integrands 1 over x minus 3 and 1 over x plus 1 are both going to follow the logarithm rule for derivatives. And so we'd be able to find the integrals of those right from there. Okay, so we're going to do two integrals examples in this video. And the rest of them, the rest of the examples in the notes will be filled in and put on Canvas also, but I'm going to start with just demonstrating two more in the video. Okay, so I've got, I'm going to skip to the one where we have the integral, and I've got the integral of 1 over x squared minus 5x plus 6. So the first task is to just key in on that integrand. Notice that it can factor down to the quantity x minus 2 times x minus 3. And we're going to try and make partial fractions out of this. So something will be over x minus 2 and another number over x minus 3. And if I put those together, it would be a is going to multiply by x minus 3. B is going to multiply by x minus 2, and it's all going to be over x minus 2 times x minus 3. So now the key equation I'm going to work with is to take the numerator of the original fraction, the 1, and set it equal to the numerator expression over here. A times x minus 3 plus b times x minus 2. And we'll take turns picking different values of x that would eliminate either the a term or the b term. So if I'm going to solve for a first, we're going to let b be eliminated by letting x equal 2. So now the equation would be 1 equals a times the quantity 2 minus 3. And so a would be 1 divided by negative 1. So I'll just kind of make a note of that. And then if I wanted to eliminate a and solve for b, I would want to let x equal 3. So my equation now is 1 equals a is going to get multiplied by 0, and b is going to be multiplying by 3 minus 2. And so b times 1 equals 1 means b equals 1. Okay, so what that allows us to do is write the original integrand as the combination of two partial fractions. The term that has x minus 2 has a numerator of negative 1. And I'm actually going to write that one second. Now I'm going to put the positive 1 in the front. So I'm going to write 1 over x minus 3, and then minus 1 over x minus 2. And if it's more helpful to you to write this as two separate integrals now, that's fine too. So I'm going to go ahead and do this. If after doing this a couple times you don't need to rewrite it as two separate integrals, that's fine also. So now in this side, each of these antiderivatives or integrals is going to be done with like a u substitution. So in the first one, if you let u equal x minus 3, so just in this side, u might be x minus 3, and then du is dx. So you can tell that makes this integral du over u, and so that's the natural log of the absolute value of u, or the natural log of x minus 3. And likewise, on this side, you would do a different u substitution. U would be x minus 2, du is 1 dx. So that's also du over u, and so the antiderivative is the natural log of the absolute value of x minus 2. So we could, of course, just leave the answer like this, but since there's just two logs subtracting, you could also write it with the logarithm properties as the log of the first quantity divided by the second quantity. Either answer is acceptable. And there we'd be done right there. I'm going to skip to this last integral here. The main reason we're going to focus on it is because it has something different. The degree of the numerator is actually bigger than the degree of the denominator, which is going to require that we simplify this fraction first. Essentially, this is like an improper fraction where we would want to split it into a whole number and a fraction part. So similar to things like this. The fraction 10/7 we know can be written as 1 3/7 because 10/7 really means 10 divided by 7. And if I wrote it out like a long division problem, 10 can divide by 7 once. And if I do long division algorithm and subtract 7 now, which is 1 times 7, the remainder is 3. And with nothing else to bring down, then the quotient is 1, and then the fraction part is 3/7. Okay, now I'm just going to erase that, and we're going to go and do that same thing with our fraction. Okay, so we're going to take the numerator, which is x squared, or sorry, cubed. Now, don't forget we got to sneak in a x squared term, which will be 0x squared plus x minus 2, and we're dividing that all by x squared minus 4x minus 12. So we have to do this long division to break this integral up a little smaller. So the first step is x cubed divided by x squared, which is x. And now, just like in regular long division, we multiply this by the divisor and write it underneath. So x times x squared is x cubed. X times minus 4x is minus 4x squared. And x times negative 12 is negative 12x. And the next step is to subtract. Now here's where you really want to be careful because there's already some minus signs here. But as you go down the columns, you always have to subtract, which means in two of these, we're subtracting a negative number. Don't forget that. So in the first column, it's x cubed minus x cubed. That's 0. Now here's where you want to be careful. This is 0 minus negative 4. And notice we said minus a negative, so that means we're really adding 4 to make positive 4x squared. And this is 1x minus negative 12, so now that's like doing 1 plus 12, and we're actually going to get 13x. And then we have the minus 2 to carry forward here. So the last round of dividing is to divide 4x squared by x squared, and that's going to get us a positive 4. And now we multiply that down. So 4 times x squared, 4 times negative 4x, and 4 times negative 12. And as we subtract, don't forget we're subtracting negatives again on two of them. 13 minus negative 16 is actually positive 29. And then negative 2 minus negative 48 is actually plus 46. And now that the remainder has a smaller degree than what we're dividing by, this is where we stop the division part. So the fraction is the fraction 29x plus 46 over x squared minus 4x minus 12. So far, let's just summarize what that has done so far. So what that has done so far is let us take the original integral, this big fraction, and split it into a couple of parts. X plus 4 plus this fraction 29x plus 46 over x squared minus 4x minus 12. So now the first two terms we're not going to have any problem with. We can integrate the x and we can integrate the 4. Now what's going to have to happen over here is this is where we do our partial fractions. Okay, so we're going to spend a little time now finding the partial fractions of this. So my denominator factors down to x minus 6 times x plus 2. So I'm going to have a fraction with something over x minus 6 and another something over x plus 2. And that has to make 29x plus 46 over x minus 6 times x plus 2. And now to combine the a and the b properly, a is going to have to multiply by x plus 2, and b is going to have to multiply by x minus 6, all to make 29x plus 46. So we'll start by solving for the a by letting b equal 6, or x equals 6. So that makes, if x is 6, this is going to be 8, so 8a. And over here, if x equals 6, we have to do 29 times 6 plus 46. I'm getting 220 for that. So a is going to be 220 divided by 8. And I'm getting 27.5. So we're actually going to write that as 55 over 2. Now to solve for b, we want to let x be negative 2. I'm sorry, running out of room here. If x is negative 2, b is going to get multiplied by negative 8. And now we'll check the other side here. It'll be 29 times negative 2 plus 46, and that's negative 12. So this is going to be 12/8, which is 3/2. So our final rewriting of the integral is going to be x plus 4. And then we're going to have the fraction 1 over x minus 6, but it's going to multiply by 55/2. Sorry, we're kind of running out of room here. And then the other one that has x plus 2 is going to multiply by 3/2. And so now these are the 4 things we have to find the integral of. Now 2 of them, just simply use the power rule or the constant rule. So the integral of x is 1/2 x squared. The integral of 4 is 4x. Here we're going to have 2 logarithms. So in each of these, like u is going to be x minus 6. And so this is going to be 55/2 times the natural log of x minus 6. And then we're going to have 3/2 times the natural log of x plus 2 plus c. So I kind of ran out of room, but there we go. Okay, I hope this helps. Again, the main emphasis was kind of the algebra lesson about how to split the large fraction into the partial fractions. Once you can do that, the integral is the easy part, I hope. Hope this helps you guys, and we will see you back here for the next lesson in a couple days.